Hi everyone, and welcome back. In this video, we're going to look at the standard normal model and also the normal model and the empirical rule. There is no universal standard for z-scores, but we do have a model that shows up a lot called the normal model, and we like to use the normal model to make estimations when we can. Normal models are appropriate for many distributions whose shapes are unimodal, so they have one mode, right? One peak, if you look at their histogram, and roughly symmetric. Some examples of normal models could be like if you were to take the students who took the SAT, if you took their scores and you were to create a histogram, you would have an approximate normal curve. It would be unimodal, and there would be symmetry, okay? Anytime you take large populations like the heights of all males, it would come out approximately normal. The weights of males, it would come out to be approximately normal. Not every distribution is normally shaped though. And if it's not, we can't make it normally shaped. But also it's a little bit more involved to try to make estimations from it when it's not. So we like when we have distributions that are normal. It's very common and it's very useful. So fortunately, the distributions that are shaped normal provide a measure of how extreme a z-score is. Here's some specific notation that you should be familiar with in this book. When you see a capital N, it stands for normal model. And then remember our two Greek symbols. This is the mean, mu, and then sigma is our standard deviation. And remember, those are your population mean and population standard deviation, which we refer to as parameters. Both mu and sigma are not numerical summaries of data, like the statistics y bar and s. Remember, y bar is your sample average, s is your sample standard deviation, okay? But rather are numbers we choose to help specify the model. And as I mentioned, those numbers are called the parameters of the model. If we model data with the normal model and standardize them using the corresponding mu and sigma, we still call the standardized value a z-score. We talked about in the last video when we shift the mean to 0 and rescale the standard deviation to 1, we end up with what's called the standard normal model. Okay, also known as the standard normal distribution. So in other words, it would be capital N 0, 1. That refers to the standard normal model where the mean is 0 and the standard deviation is 1. And just remember, standardizing will not change the shape of the distribution. So if it's not unimodal and symmetric to begin with, standardizing won't make it normal. To use the normal model, we want to check what's called the nearly normal condition. And what that involves is we want to check that the shape of the data's distribution is unimodal and symmetric. And we want to check this by making either a histogram or a dot plot. You don't really want to use a box plot. Box plots don't really show shape. You can see symmetry in a box plot, but you really don't know much more than that. Okay, like for instance, if the shape was uniform or unimodal, it's really difficult to see that in a box plot. Please recall that the normal model gives us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. In a normal model, about 68% of the values will fall within one standard deviation of the mean. About 95% will fall within two standard deviations of the mean, and approximately 99.7% of the values will fall within three standard deviations of the mean. In statistics, we call this the empirical rule, also known as the 68, 95, 99.7 rule. And here you can see a picture of the normal model. This is a normal curve. Okay, a couple features. The curve actually extends forever in both directions. So it goes towards positive infinity on the right, negative infinity on the left. But after 3 standard deviations, we kind of don't bother continuing to draw the sketch because the area is so small. It's basically 0. In the middle, we have our mean, which remember is 0. That's our standard normal model, and our standard deviation is 1. So we can see 3 standard deviations above the mean all the way to 3 standard deviations below the mean. And what's special about the normal model is approximately 68% of the values will fall within 1 standard deviation of the mean, 95% will fall within 2 standard deviations of the mean, and then 99.7% fall within 3 standard deviations of the mean. And that's helpful when we're trying to make some estimations. So in this problem, a study of men's health measured 14 body characteristics of 250 men, one of which was wrist circumference in centimeters. The mean wrist circumference was 18.22 centimeters, and the standard deviation was 0.91 centimeters. The histogram of all 250 values looks like this. Will the 68, 95, 99.7 rule provide useful percentages from these data? And about how many of these men does the rule predict to have a wrist circumference larger than 20.04 centimeters? So basically, we first look to see if we can use the 68, 95, 99.7 rule or empirical rule. I need to check the nearly normal condition, which says that I have a histogram or a dot plot, and it's unimodal, which this is, and roughly symmetric. So that means it is okay to use that rule. So yes, because the distribution is roughly unimodal and symmetric. Okay, so if that's the case, I can use it to predict something. So I'm looking for here about how many men does the rule predict to have a wrist circumference larger than 20.04 centimeters. Okay, so I know that I'm basically looking for 20.04, like maybe right about there, and I'm trying to find the area to the right of it. Okay, so if that's the case, I need to figure out where, what percentage of the data fall above that, okay? So in order to do that, the entire curve I know is 100%. If I can subtract out a piece of that curve, I'll be left with the red part, okay? So how would I do that? Well, if I kind of estimate here, here's the center, which is about where the mean is. So if I go roughly 2 standard deviations to the right and 2 standard deviations to the left, okay, so if I count 1, 2, 3, that's about 2 standard deviations over, and then 1, 2, 3, that's another 2. So if I have another flag here, I know then that from one flag to the other, it's 95% of the data. Okay, so how does that help me? If I take 100%, which is the whole curve, and subtract out 95%, it leaves me with 5%. Okay, well, what does that 5% represent? It represents there and there. The curve, remember, is symmetric. So it's the same area on this side as it is on the right side, okay? So since both of these are the same, I need to take this 5% and I need to divide by 2. And 5% divided by 2 is 2.5%. So that represents 2.5% of the 250 men. Okay, will have a wrist size larger than 20.04 centimeters. So if I need to do 2.5% of 250, I want to convert 2.5% to a decimal. Remember, to do that, we're going to divide by 100, which essentially just moves the decimal to the left 2 places. So 2.5% is just 0.025. And then of means multiply, and I'm going to multiply by 250. And when I do that, I get 6.25. Okay, so you can't have 0.25 of a person. So we would say that approximately 6 men have wrist sizes larger than 20.04 centimeters. Okay. If you could, please pause the video and you can try the next problem. And there's a set of them. You're going to use the empirical rule for each of those problems to calculate some information. As a group, the Dutch are among the tallest people in the world. The average Dutch man is 184 centimeters tall, just over 6 feet. And the average Dutch woman is 170.8 centimeters tall, just over 5 foot 7 inches. If a normal model is appropriate and the standard deviation for men is about 8 centimeters, what percentage of all Dutch men should be over 2 meters, or 6 foot 6 inches tall? Okay, so the first thing I notice here is we have all different labels. We've got meters, feet, centimeters. We need to get a consistent label going on here, okay? So what I'm going to do is I'm going to take 2 meters and I'm going to convert that to centimeters because everything else is in centimeters. Okay, so how do I do that? Well, I just need to know that there's 100 centimeters in 1 meter, right? So what I would need to do is just take 2 times 100. So there's actually 200 centimeters in 2 meters. Okay, now that I have my labels the same, it's the same as this, and it's the same as this, etc. I can do some conversions here. So I'm going to take my 200, and I'm going to find the z-score. Because I want to see like where does this fall on the normal model? Okay, where would a Dutch man that's 2 meters tall fall? So now I'm going to divide. I would end up with 16 divided by 8, which is 2. So I know that a Dutch man that's 6 foot 6 or 2 meters tall is actually 2 standard deviations above the mean. Okay, but now I want to find what percentage of all Dutch men should be over that. So I'm looking for, in other words, the probability that z is greater than 2. Okay, the probability that you would have a man that's taller than 2 meters. So again, I can use my empirical rule. If I was to draw a fake invisible flag here on the opposite side, okay, I would know that between those two flags is 95% of the data. Okay, so 95% of men would fall within 2 standard deviations of the mean. So that tells me that if the whole curve is 100%, if I subtract the 95, I get 5%. And remember that the 5 is actually divided up among the 2 sides. So I would need to then divide by 2, and I would get 2.5%. So what does that mean? And it means about 2.5% of Dutch men should be over 2 meters tall. Suppose it takes you 20 minutes on average to drive to school with a standard deviation of 2 minutes. Suppose the normal model is appropriate for the distribution of driving times. How often should you arrive at school in less than 22 minutes? Okay, so the first thing I want to do here is I want to draw my normal model. So you can sketch it. And in the middle is our 0, okay? And then we've got 1 standard deviation to the right, 2 to the right, and 3 to the right. And then if we go backwards, we've got 1 below, 2 below, 3 below. So I need to figure out where's the 22 go. So I need to come find its z-score. So remember, z equals the value minus the mean divided by the standard deviation. And 2 divided by 2 is 1. So I know that right here is where the 22 minutes would go. That's where z equals 1. How often should you arrive at school in less than 22 minutes? So if I'm looking at less than, I am looking at the area to the left of that. Okay, so I want to figure out what is this area. And since I'm using the normal model and I'm exactly at 1 standard deviation, I can figure this out. So something to remember is that between the 2 red flags here, okay, if you'll recall with the normal model, 68% of the data fall within those 2 between 1 standard deviation above and below the mean. Okay. Well, remember, one of the properties of the normal model is it's symmetrical. There's symmetry. So if you picture us dividing this normal model up, right? Would everyone agree that this is half of the model right here to the left of it? That's 50%. So that takes care of from the 0 to the left. That's 50%. I just need to find this piece here. So in other words, I know from here to here is 50% because from here to here on the right side is also 50%. Okay, so now I just need to figure out this little sliver right in here. Okay, well remember, if this is 68%, 68 divided by 2, why am I dividing by 2? Because it's symmetrical. 68 divided by 2 is 34. So really this 68 is broken into 34% and 34%. So now to figure out how often you should arrive at school in less than 22 minutes, it's just going to be 50% plus 34%. And 50% plus 34% equals 84%. So approximately 84% of the time, you should arrive at school in less than 22 minutes. How often should it take you more than 24 minutes? Okay, so again, you're going to first want to find the z-score. So it's the value minus the mean divided by the standard deviation. And this time we get 4 divided by 2, which is 2. So now we know that we're 2 standard deviations out. So if I was to shrink this, let me move it, and then let me draw a new picture for you. Okay, there's your normal model. Here's 0. And I know that I am now 2 standard deviations out. And I apologize, my marker is acting up. Okay, so there's 2 standard deviations out. Okay, and we already remember the empirical model, right? That if you go 2 standard deviations above or below, it's 95% of the data. We've seen this before. That leaves 5% total on either side, right? So 5 divided by 2 is 2.5. So how often should it take you more than 24 minutes? We're looking for this side now. And we know that in order to find that, we would do 100 minus 95, which is 5. And then we divide 5 by 2, and you get 2.5%. And again, the reason we're dividing by 2 is because both of these sides are symmetric. They're the same. So there's 2 of them. Now, we just did all that work. Do you think the distribution of your driving times is unimodal and symmetric? I would say no, because there might be traffic incidents or some outliers, accidents, a traffic light broken, whatever. I would say it would be more skewed to the right. And the reason is because, the traffic incidents would increase the time, right? So I would say probably not. It's likely skewed right because of traffic incidents and some outliers. So those incidents would increase time, we would assume. So what does this say about the accuracy of our predictions then? So if we assume it's skewed right, the normal model would not be appropriate, right? So the percentages we predicted would not be accurate. So the percents are not accurate if the distribution is skewed right. And that is the end of this video. Please stay tuned for the next video where we talk about what happens when you don't get a z-score that's a perfect 1, 2, 3, or -1, -2, -3. If you have any questions, please reach out. Please enjoy the rest of your day.